Hello, my name is Elisa Caulfield, and I'm the academic director of the Notre Dame Global Center here in Kylemore in the west coast of Ireland. And I am welcoming you to our second installment of the new Global Dialogues series, where we're going to spend this semester discussing the water crisis and travel from week to week, country to country, global center to global gateway to global center. And it's our hope that over the course of the next few weeks that we build a virtual community and connect with people globally to reflect upon the material that has been presented on the ThinkND platform. We've designed the global series dialogues to have as much interaction and engagement as possible. So we have these opportunities to engage with the platform. There's the ThinkND LinkedIn board where you can have post subsequent questions. And then we have these live sessions that are happening weekly in which you can engage with our faculty and our partner institutions in which we collaborate with further research. So we hope that you will find this experience with this series to be insightful and engaging, and it's our contribution to the academic forum, the care for our common home. We hope that you stay connected not only to us here via the Kylemore network, but also with the wider global Notre Dame International Network and also the ThinkND Alumni Association. At this time, I want to thank our co-sponsors for this particular series, the Global Dialogues, that being Notre Dame International, the Office of the President, the Office of the President, all of the university colleges and schools that have contributed their faculty to this extensive series, and of course, the Notre Dame Alumni Association. Each week, we've had faculty from Notre Dame contribute these videos in which you have the opportunity to hear on the exciting work that we're working on as an institution and to really engage internationally with the research that's being done around the globe. This week, I'm delighted that we have the opportunity to discuss the effect of coastal storms on with coastal border deposits along the coast of Western Ireland. As a brief description to the work that's being done, big waves from coastal storms cause rocks to be lifted out of the bedrock and become displaced onto the Irish shores. This dispersion of these boulders varies based on the boulder's weight and elevation. It's by taking a closer look at these boulders that we can reveal a record of climate change and storms throughout history. Looking to the future, this will be further affected by climate change impact on our coastal shores. With increased storm intensity, this project will be of a higher probability of damage to human infrastructure. With us today, we have Professor Andrew Kennedy and some guest panelists from local institutions that Professor Kennedy has worked with. Professor Kennedy has discussed his research on the ThinkND platform. And if you haven't had a chance to listen or watch his video, I encourage you to do so on the ThinkND Global Dialogue series. Professor Kennedy is in the Department of Civil and Environmental Engineering and Earth Sciences, and he is here to discuss the topic of coastal border displacement in Western Ireland. Professor Kennedy, thank you and welcome.
Thank you, Lisa. I'm glad to be here.
Also on our panel is James Hedrich, who's from the School of Mathematics and Statistics at the University of College, Dublin. His research is based on fluid mechanics, geophysical flows, environmental industrial problems, and particulate-laden flows. He's a member of the Earth Institute, and I'd like to warmly welcome James, who is actually dialing in from Gorey this afternoon.
Hi, good afternoon. Thanks for the opportunity.
Hi, Mary. Our third panelist today is Mary Burke, who is a geomorphologist from Trinity University in Dublin. Her research interests lie in the areas of extremes, and her goal is to better understand geomorphic processes in extreme environments, such as the deserts on Earth and on Mars, and during extreme events such as floods and mass wasting. To start off then, I'm going to ask Professor Kennedy to describe his lab and the research that he's doing and how he's come to work in the west coast of Ireland. Professor Kennedy.
Okay, so thank you again, Lisa. I would say that the work I do could be described as coastal science and engineering very broadly. This is waves, storm surge, erosion, and damage to communities, things like that. And the way I got to the west coast of Ireland was a very roundabout way. And I have to take you back to 2013. Typhoon Haiyan hit the Philippines, and I went to the Philippines with a Japanese team to measure the inundation there. And we were measuring the high water marks all around the coast where it made landfall. And we were on this little coastal road. There are trees down everywhere. We were climbing over the trees. It was really, really hot. And then all of a sudden, Professor Nobu Mori from Kyoto University said, hey, that doesn't belong there. And there was a giant boulder sitting on the road. It had started off in the ocean and it had moved up about 20 feet of elevation and was sitting part way across the road. And it was pretty obvious this was interesting. And we started looking around more, found more and more. And then started working with Rona Cox, UCD, in the west coast of Ireland, and James and Mary and Frederick Diaz, and it's just all gone from there.
I wonder, Professor Kennedy, if you can describe a bit about the characteristics of your research in Ireland and why is Ireland unique in this particular topic? Okay,
well, the Irish coastal boulders are, I would say they're unique because there are so many of them, and they are forced by winter storms every year. For example, in the Philippines, they were only forced by giant typhoons, which don't happen all the time. But in Ireland, winter storms happen many times a year. And as Lisa's just said, you're getting one today and another one tomorrow or the day after. So everything is happening. And I'll share, can I share a picture, Lisa? Okay, so I will share the screen. Screen one. Oh, come on. Come on. And now PowerPoint isn't working, of course. Just a minute.
We can see that, Andrew. We could see that.
Oh, you can see the, okay, I can't actually.
Well, we could. Now we see a beautiful picture of Kylemore, I think, is it?
It's the lake, no. I think. The lake at, I think it's the lake at, there we go. There's the.
Are you seeing the boulders now?
Yes.
I see people on boulders, yes.
People on boulders. So this is an example from the west coast of Ireland. And it's these rocks, you can see them in comparison to the size of the people. They're very large. Some are even much larger than this. Some are many, many times larger than a person. This is photo was taken by Rona Cox of UCD. And these deposits are everywhere, and they are a record of what has happened over the past couple of hundred years, if we can decipher it. And we can get to these boulders pretty easily in comparison to some other places. They can be studied. We can see if they move every year. We can do experiments. For example, one experiment we want to do would be to take some of these boulders and push them closer to the edge, so they're more likely, the edge of the cliff or the coast, see if they're more likely to move. And in that way, we can see exactly the conditions that cause them to move. So Ireland has both the numbers, the reliable conditions that cause these boulders to move, and it's very accessible compared to a lot of places where you have to hike over little mountains to get to the coast. So these are some of the things that make Ireland a very good place to study these deposits.
Andrew, what classifies a boulder? Like when you're looking at this picture, there's extreme kind of sizes, there's smaller sizes. I guess, how do you define the boulder, and what's the sort of smallest size it could be, and to the extent of the largest size you would look at?
Well, the largest size is whatever the biggest size is that moves. And that can be a couple of 100 tons at the very, very largest sizes. The smallest ones are, well, there are definitions of the smallest sizes of a boulder, but very often you look at the farthest inland that things go, and whatever the largest size is that you can show move, a couple of 100 meters inland, those are the sizes that you care about. So people generally care about the biggest ones because they're the hardest ones to move, but the smallest ones can move further inland, and so sometimes they're very useful to study as well.
I might move to Mary now, because Mary also in her video on the ThinkND platform mentioned the uniqueness of Ireland's coastline. And I wonder, Mary, if you can further elaborate about the Irish coastline and what makes it so unique. This was one of the questions that was submitted by our students.
Yeah, it's a great question. Well, I might be a bit biased. I do think that these particular deposits are some of the best in the world for a number of reasons. And I'll get onto the coastline in a minute, but just you asked a very specific question about the boulder. And it has been defined on a numerical scale about what makes a rock a boulder as opposed to a cobble. And we measure what's called the intermediate axes. Like if you pick up a ball, you can measure the length, the width, and the depth of any object. And so we do the one in the middle. And when that is less than 4 meters and greater than 64 centimeters, we classify it as a boulder. So you'll have heard of things like sand and silt and gravel. They're all a specific numerically defined size. It's not just, oh, I've got sand, there's sand on the beach. It's referring actually not to the quartz yellowy looking substance. It's the stuff behind me actually. That's fine gravel and pebbles. So the Irish coastline is, well, okay, let's talk about where we are. Let's be a geographer about this. We are in the Northwest Atlantic. We are basically this island of Ireland, and particularly the West Coast. We're at the frontier of all of the weather systems that are generated often down in the Gulf of Mexico, and one way or another will swoop up the east coast of America and come across the Atlantic, generally declining in energy. So a lot of the hurricanes that are generated in that little, that large area of warmer water reach us as intense depressions, which bring massive winds and rains with them. And our island, which is viewed as being rather small in the context of things, receives that energy full bore first off, especially if the system crosses over us. So it may diminish a little bit as it crosses over us because of the mountains create diminished energy. They take away some of the energy from these systems. And so our island is remarkable for where it's located. Secondly, the configuration of the coastline. It is what we would use the term crenulated, and that means intensely kind of squiggly. Like if you were to take the length of it, it is, and I think I said this on the video, the length of from here to Notre Dame, here being Ireland. I'm in Ireland at the moment. And that's an enormous length when you look at it, because it's kind of a couple of 100 kilometers, like as a crow flies. So it's very important that, and the other aspect of it is that crenulated form, two-dimensional form, not only leads to a very long length, but it also leads to these little funnels of energy, these bays. And when wave energy comes into these bay forms, it is accelerated and accentuated at the apex, at the point of meeting the land, right at the inner side of that bay. And that's where we do find a lot of these very coarse grained is what we call them, but large boulder deposits. And the interesting thing is that they came from right in front of them, most of those boulders. They were snapped up from the rock that's exposed right where the waves broke, and then they're moved inland. And that's where James's work comes in to try and model, okay, well, what was that energy like? And how exactly does that happen? How does a wave break off a big chunk of rock and then move it across the platform?
We've been told, and for people who are around the globe tuning in today who might not be too familiar with Ireland's climate, it's been characterized as very temperate. When we say that, what do we mean by that, Professor Burke? And to what effect does a temperate climate affect your research with regards to this, work that you're doing? If it's temperate, it would seem that you don't have much extremes. And so how, by the definition of, with storms, would there be that many storms here in Ireland?
Yeah, it's a great question. And it refers to statistics, really. So temperate it refers to our latitudes. We're in the mid latitudes, up in the 50s, the mid 50s in the Northern Hemisphere. We're in a temperate zone because we have mean annual temperatures that exist in a certain kind of range, and rainfall that also exists in that range. And it contrasts completely with other countries that you're visiting. For example, you mentioned that you'd been in, where was it, Nairobi where were you last week?
Last week, yeah, yes.
And you're going to India next week. Now, both of those places have climates that are in the extreme, like you have extremes of rainfall and extremes of temperature. And by that, we mean over 1 meter, 2 meters of rainfall a year. In Ireland, we get just over 1 meter, and it's spread out over the whole year. So it's not only how much you get, it's like when you get it. Is it seasonal or monsoonal? So, we're kind of in a bit of a Goldilocks zone, not too hot, not too cold, just right. A lot of people here wouldn't agree with me, for instance, too much, but we're sitting in this boiling cauldron of bubbling, stormy oceanic waters. So our annual climate is fine in terms of its means, but then we do get extremes. And I think there's been a massive wake-up call in terms of climate and potential climate change in Ireland, because since, as Andrew mentioned, in 2013, the Hurricane Hyatt, we've had all of these huge storms, these depressions coming across and hitting the Irish coast, and we've gone, hang on a second, what is this? We're not used to this. And we even had this almost hurricane come up from the Azores last year, the year before. So we're really beginning to look at what is the reality of our climate, and particularly our wave climate. And there's lots of models that suggest things are going to get a little bit more fierce. The waves, when they do happen, will be bigger. So we have to prepare ourselves for that. And that's why the work that myself and James and Andrew do and plan to do, maybe with these experiments of Boulders, will really inform us and help protect us in these different models, these projected models of climate change, wave climate change.
Just to follow up to your video, you mentioned that sometimes smaller storms can cause more havoc. Can you further elaborate what you mean by that, and how is that particular to Ireland?
So there's a couple of things there. One is me being a complete nerd and getting deep diving into my geomorphology. And there's a concept there that, big things happen and everybody takes notice and it's, oh my gosh, what a catastrophe. And then there's all these small little things. It's a bit like the hare and the tortoise. You've got these small events that just kind of peter along, and once every 2 or 3 years, they do a little bit of work, but not so much that you'd notice them. And so when it comes to coasts and coastal floods, was actually an American hydrologist, I'm going to call him, I don't actually know whether he was an engineer or what it was, came up with this concept of nuisance floods. Now, nuisance floods are these frequently bothersome events that will cut the water off as you're trying to get to work or your kids to school. And there'll be a cost associated with that. And the idea is that you accumulate all those little nuisance events, and they end up being more expensive and perhaps more damaging in the long term than the once-off big, massive event. And we're still working out that. But getting back to me being a complete nerd in terms of geomorphology, the work that the smaller events do, and this was particular to the west coast of Ireland, we monitored a few small boulders. We need to get and monitor the big ones. And we watched them just as the tide came in and went out. And we were really surprised that the changing tide and the waves that were generated on a normal day in September got those huge boulders. Now, my students, God love them, and the students attending here might be able to sympathize. I got them to move the boulders. It was like fun and hilarious, and oh my gosh. And they dragged them across using marine litter. They popped the boulders on that and dragged it across the platform. And we couldn't believe that they moved. And then when we went the next morning and we set up cameras and everything, we saw that not only had they moved, so there was sediment transport, but they'd left all these scratches and grooves and smashed bits of rock on the platform. And that suggested to us that each and every day, those rocks are doing a little bit of work to wear away that bedrock, and we never thought about it in that way before. So they're not the nuisance events, but they are smaller events doing a lot of work over a longer geological timescale.
So is it fair to say, Mary, that Ireland is actually an ideal place to do your work and your research?
For these coastal storms, I would say absolutely. And Andrew we've got the energy, we've got the rocks, we've got the undisturbed coastline. It is inhabited, but there's a lot of free space there. And it's accessible. We can walk there. And a lot of the problems we have in doing research in areas that have extreme events is to get the equipment in there reasonably cheap and be able to access it and get the data from it, and also have it so that nobody comes in and messes with it and damages it. Just out of boredom or whatever reason they might have. So we seem to be meeting and fulfilling all of those field site criteria. And then, of course, we have the expertise in Ireland, like James, and then people coming from the United States just as well. So, yep, it's the best place in the world, in my opinion, to do this research. And it's been unstudied. This is a frontier of science. No one is looking at this stuff.
Well, you mentioned James and Professor James Heritage. I'll bring you in now too, just to kind of further elaborate on your own video and what you mentioned on the models. And Mary alluded to this. What exactly are models, and what is the model physical process that you mentioned in your video?
Well, when it comes to modeling the process, I guess it's really there are multiple processes to be modeled in it. As Mary was discussing, you have these, you'll have storm waves generated by the passing storms, and they propagate in towards the land, and then they get funneled in these bays, and then they start to grow larger in amplitude. So just in that process is one thing. How does a storm wave that's generated out at sea, what does that then look like when it actually reaches the coast? And a lot of that is to do with not just waves interacting with each other, but even the individual bathymetries of different parts of the coastline. So what do I mean by that? It's just the underwater topography. As the water gets shallower and the wave is approaching the coast, then it actually gets amplified and grows in amplitude. So you have nice waves being generated out at sea, propagating in, and then they reach a surf zone and they start running up cliff faces. And really, how do they get over the cliffs is just one aspect of modeling, which is very much in the wave mechanics kind of field. But then once it actually gets over the cliff, these kinds of waves end up in a completely different regime, where they're almost like rushing bores of water that then smash into these big boulders. And this is where you start asking questions like, what kinds of impacts do actually create motion? What are the relevant criteria for one of these blocks to move, and how do the hydrodynamics of this very complicated process, where there's not just water, but there's trapped air in the water, and this increases pressure, and lots of very, very interesting questions to do with that. And although you've seen in some of those pictures that those boulders actually have some remarkably nice shapes that do simplify the process, they can be very nice and rectangular, which makes some of our lives a bit easier. But actually, even still, the reality of the situation is still very far from ideal. So there's lots of processes going on there. And then the actual transport then is, again, another, do they flip over, and what kind of transport properties do they have, is all very, very interesting questions to look at.
In your video, you talked about measuring waves up the cliffs. So one of the questions that our students submitted in advance are, what are some of the most dramatic or extreme measurements you've taken? And are these unique to the Irish coastline based on your experience from your travels around the world? And have you experienced the similar wave measurements that you've seen here elsewhere? So
in some of the projects I've been involved in, we've done some wave measurements, but we've been doing them slightly not on the exact coast, but on what we might call the near shore, which is maybe a little bit, like a kilometer or so off the shore, where you can still get measurements, but the device you're measuring won't be kind of destroyed by the wave itself. And that's the risk that can happen with actual, if you're measuring it on the cliff itself, because as the wave comes in, it could do some damage to your equipment itself. So the measurements on the cliff itself are hard to come by. We have done a little bit where we've put on, once the wave gets over the platform and gets onto the shore, it's a little bit safer. Let's put it that way. And you can put some, for example, you could put some pressure sensors there to really see what the waves look like on top. But we do even just in the near shore, we've measured waves that are kind of 10 meters high in a depth of just over 40 meters. So when you think of what that really means, it's kind of a huge displacement of water for what's actually there. And it's that transition from the near shore to the onshore that's a really critical and one that is very much what people are trying to do at the moment.
And I guess if you can just give it to us, like sort of contextualize the Irish waves to other waves you've measured, is there comparative measurements to say like it's worse here, or can you kind of give us a bit, sort of better context of that?
Well, very much. So a lot of the platforms that we deal with, so these are very exposed platforms. And in terms of what work gets done, where you find these boulder deposits, the height of that platform is very much will tell you exactly how high the water can get up. So some of the platforms are maybe 16 to 20 meters, and we have some platforms that are 30 meters and some that are 50 meters high. So that's really waves are getting up that high and causing damage there. So it's really going to be limited by what your actual shoreline looks like and what the height of the cliffs there are. And there are boulder deposits, well, kind of internationally. And there are some in places like Scotland that are also of a similar kind of height above the water. I can't actually, I don't have a figure to mind for some of the other countries where there are lots of boulder deposits. But when we're talking about how high are these waves getting, I mean, they're getting over 30 meters height over cliffs.
I might move back to Professor Kennedy then and say, just kind of given the context of climate change and these boulder displacements, are you in your with your lab and the work that you've done, are you seeing a sort of increased frequency to this, and are you seeing I guess a higher demand on the research that you're doing in your lab, and would you what is a priority of your lab at the moment?
Okay, so in terms of are we seeing increased frequency, I guess the answer would be not yet. Right now, what our lab's biggest priority is trying to link the boulder deposits to a climate, both the environmental climate and then the wave climate. And then if we can do that, we can do two things. One is we can predict what might happen given climate change predictions in the future. If this happens, how will this affect waves? How will this affect the inundation? Will it get to places that are not inundated now? That is a major area of interest. And I'll say that the boulder deposits studies, as Mary said, is a very, very young field. It's a very young field. And so there are a lot of things that we know we will be able to do that just haven't been done yet. The second thing that we try to do with climate is we try to decipher, given boulder deposits somewhere, and probably not Ireland, where we don't know what actually happened, what were the climatic conditions that caused this? Was it a giant hurricane, a giant winter storm, or was there some unknown tsunami? And this is a very major question in the coastal boulder deposits. Finding boulders where you're not quite sure what happened and then trying to decipher it. So if I can do a share screen again, I will show you something else. Okay.
Yeah, please, by all means. Yeah, go ahead.
Okay. Oh, come on.
As Professor Kennedy is teeing this up, I just want to remind the group that's on the call that you're more than welcome to ask a question via the chat function. Just put it in the chat function and I can pose it to one of our three panelists. So please use the chat function.
Okay, thank you, Lisa. So are you seeing the gigantic, monstrous boulder there? This was not by a storm wave. This is on Tongatapu Island, which is the main island of Tonga. And what this suggests, this is a coral boulder, and you can find the coral parts there, and you can see where it came from. That was deposited by a giant tsunami from a volcanic eruption. And things like this is a very extreme example, but things like this from storms and from tsunamis, you can use those to say, if this happened in the past, we can try and find out how often it happens and how often it's going to happen in the future. And if you remember in the news a couple of weeks ago, a giant underwater volcano exploded just offshore of Tonga. And the parts of the island chain were inundated again by tsunamis. Fortunately, they weren't as large as the one that generated this. But what this particular thing did was it gave people an idea that they could use that to infer what happened at some point in the past. So these boulders last for a very, very long time. Vegetation decays, other things go away, but boulders stay there for hundreds to thousands of years. So both in Ireland and other places, these are things that we can use to figure out what past climates were like. And this is another big area of interest. Mute.
Yeah, sorry. Professor Kennedy, you also showed in your video the very dramatic image of a woman on the wormhole on the Aran Islands, which is a place we take our students to quite frequently. And these sort of rogue waves that we see in Ireland have claimed many lives, I suppose, in Ireland. And there's always a sort of a caution to those people who are kind of cliff walking to be very careful of these sort of impact of these huge waves. I was just wondering that from that wormhole and how it's created, if you could give us a sort of sense of why that's a special space for you and you know the unique kind of character of that square. If you could just further elaborate that for us who kind of go to see the dramatic waves but don't really know how that unique square is actually carved.
Okay, well, I'll go first. There's a very good rule, and it says never turn your back on the ocean, because there are things, rogue waves, or sometimes they're called sneaker waves, where you're somewhere and you just look inland, and then all of a sudden something comes in, and they're very dangerous. If you go on to YouTube, you'll see many videos of these. The wormhole is obviously a big tourist place. If you go on YouTube, you'll find Red Bull diving competitions there. But I guess it's not so much a super boulder place as it is just a very good place where you can show waves going at different levels. There's a lower level, which was the lower platform, which is much more dangerous. There's a bit higher level where the unfortunate tourist who survived, she was fine, was swept off, and then there are even higher levels. So it can give an idea of just how different elevations in close proximity to each other, how often they're inundated and how things behave there.
And I guess this is a very technical question, but how does wave impact actually generate boulders?
Okay, this does get technical. So when, imagine my fist is a wave and it's coming and it's hitting, it's going fast, 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 and then it hits the boulder and it decelerates very quickly because the boulder is there and it's sitting there. And when it does that, it causes a very high pressure for a short time. And that can be enough to make the boulder slide. It can be enough to make it flip over. Also underneath the boulder, there can be high pressures, which can lift up the boulder and not float it, but sort of float it, lubricate it as it moves across. So it's both very high impact pressure, and also in some cases, just if you go out and stand in a strong wind, you can feel the pressure. If you go and you stand in at the beach and waves that hit your chest, if the wave breaks on you, you can feel it's very strong. If it doesn't break, it's maybe not as strong, but these breaking waves, when they hit you, I've seen very big people knocked over by waves that were not so large. So these rapid decelerations can cause very large pressures, which move the waves. Very often at the cliff's edge, the wave will hit the underside and that flips the boulder upside down. You can see many examples of the boulder being flipped over by a wave hitting the underside and just knocking it over. So it's the very, very high pressures, and water is heavy. You don't think of water as heavy, but it's very, very heavy, especially when there's a whole lot of it, 20-meter wave coming at you at once. That's a lot of water.
And Professor Kennedy, have you ever had that experience of similar to what we saw in the video?
Not like that, no. I've been knocked down, but I have a tendency to stay as far away from the edges of the cliffs as possible. Occasionally I will do it, but I've seen too many inundations in places where I thought, I've stood in places where I thought there's no possible way any waves are getting here. And I was wrong. And I work in this area. So I've never had that happen to me, and I don't ever want it to happen to me. So no.
Well, thank you. Mary, we have another question for you from our students with regards to your work and research, as you stated yourself that you work in areas of extremes. And is it your considered opinion that extreme environments are becoming more or less prevalent in places like Ireland? And how does temperature or climate weather patterns affect the storms that you've studied? And then maybe you can, I guess, and then further to that, can you also talk about your work on the Earth's planetary surface group?
Sure. So the question is, what? How extreme?
Yeah. Like you're in your opinion, you're like the extreme. Are they becoming more prevalent in places like Ireland, or are you in your research? Are you detecting specific weather patterns?
So I'm going to have to use the research done by other research groups because I'm not a climatologist. My data is important to them, but I don't work on the atmospheric models. So they have found, looking back on records and using geology as a kind of proxy for extreme events. And I just want to mention two things about Ireland that the people attending may not know, that we have, I suppose, the longest environmental written record in Ireland, the Annals, the collection of notes, environmental and climate notes that were written down by monks over thousands of years. And the very first written down record of a landslide is from these Annals. They're tremendous, and they've been validated using, they would record eclipses and things like that we can model. So we know that the data is true. The second, I suppose, thing is that with extremes, records are key. You don't know if you have an extreme if your record isn't long enough to establish what the norm is or the average is. And so again, the research group at Notre University have put together the longest continuous rainfall and temperature record in the world. And they use students to do it. Again, I'm harping on this students as slaves thing, but they used the students in their class to transcribe down these written weather records going back hundreds of years, over 300 years, and they were able to publish that data. So, you know, it's this idea of the written word and stories being very useful to help us establish what is normal and not normal. So in answer to your question specifically, using these records and the very, very short instrumental records, which go back maybe 30 years, 100 years if you're lucky, we're able to see the trends in the data. Now, not just the models, but the data are showing that, yes, Ireland is getting warmer in its summers, droughts. We have had periods of decadal-long droughts in Ireland where water shortage was a massive issue for farming and for farming the land and for people inhabiting the land. This was back in the 1800s. So we're all kind of tentatively waiting for the next massive drought to hit Ireland. And of course, there was a drought in the 70s as well that was less extreme. We've also recently experienced the beast from the east, which was this massive cold system that moved across Ireland. So we are still kind of updating our records with the extremes. But it's also worthy to note, I spent a lot of time working in Australia, and they 2 years ago had to change the scale on which they reported their temperatures. And you'll remember that temperature recordings are recordings that are made in the shade. They're not in the direct sunlight. And they started to record in the shade temperatures that exceed 56 degrees centigrade. I don't even know what that is in Fahrenheit, sorry, but it's really too hot to be able to survive. So, you know, it's a combination, I think, of, yes, things are changing, plus, yes, we're finally beginning to record quantitatively the data. And what's helping that is not only, like, if you think about a large desert, we're not going to get a Met station out there that's going to be able to record that data, but we do have satellite data that can record surface temperatures, and we can use that. And that's really what's informing us about globally this increase in wave energies, in extremes temperatures, both warm and cold, and extremes in hydrological events like too much water and too little water. So Ireland is going along with global patterns of, you know, we're having more extremes, and the models will say that they'll become even more extreme as we go toward, like, in the next 50 and then 100 years.
You also mentioned that, like, an interdisciplinary approach to the research that you're doing, and I think this panel is an evidence of that. You know, mathematician and yourself and Professor Kennedy. So that but I was hoping you might elaborate further about this. You know, and I think this is with climate change as a whole, like interdisciplinary. When you're looking at the UN Sustainability Development Goals, like interdisciplinary work is essential to going forward. It's clearly not in one specific, you know, area of research. I just would like you to further elaborate how the importance and how you see it from your own work.
Yeah, it's essential. We're not going to make any progress, significant progress in tackling any of these issues without a broader approach to it, both from the social sciences, the science, humanitarian, medical sciences, etc. Because even if you just look at the definition of what is a hazard, it's not a volcanic eruption. A hazard is something that impedes the life, health, livelihood of humans. It's when humans come into contact with something that puts them at risk. And, you know, we have people who study rocks. We have people who study, you know, how rocks move. And we've got people who study people. And you need to bring them all together, particularly in the area of climate change, particularly in terms of hazards, because the Sustainable Development Goals are all about how our changing world and global inequalities and justice needs to be rolled out across our planet. And for that, of course, you need to understand governance and politics and people and society and cultures. Like, why are women and children so much more vulnerable in hazardous events? If you go to cultures where women are not allowed to speak to men, how can they be saved and pulled out of a river or from underneath a crumbled building? like that there's so many challenges. So anyone, like we all do our bit. I dig holes for a living, and it's, I enjoy it very much. And James models, and Andrew has this wonderful engineering mind that can bring a lot of this stuff together. But the three of us together, I'm a geographer. We represent, the future for this kind of research, because we all come from a different perspective, and our brains work differently. We've been trained differently, and that's a good thing, because we can have these really constructive discussions from different perspectives and learn from each other, and then have these original ideas as a group, this synergistic approach. That's my experience of it anyway.
I would welcome Professor Kennedy or Professor Hedrich to further elaborate to how your work complements one another.
Oh, thank you, Lisa. I would echo exactly what Mary said. There is not a single person in the world who knows enough to tackle the entire problem. I know some parts of the problem, and other parts I may think I know something about, but I don't really know that much. And that's why we need James with his models of how things move. We need Mary with her expertise in how the landscapes are formed and how they change. There are other colleagues. We have geologists who are not on the call. Rona Cox, who has very good expertise in the geology of these coastlines. We have engineers who are busy measuring everything. We have paleoclimatologists who are trying to date some of these deposits to see how old they are. So what really helps is when all of these disciplines come together, which is what we're trying to do here now and in future projects. And then when we do that, we can make more progress that we couldn't do if we were just working in our own individual disciplines. So the bringing people together is what really allows us to attack the overall problems.
And I just like to say that it might be admirable, but it's not always easy, because we do speak different languages. And that is one of the, I think, where we're all, when we step out of our silos, are beginning to learn a language that we can all understand. Like James' brain works in a very different way from my brain. I'm a visual person. He definitely has a mathematical brain. And so when we talk about something simple as a boulder moving, we're looking at it in a very different way. And so we are, and all scientists, I think, are starting to learn the language of communication in transdisciplinary modes as opposed to our own disciplines.
Yes, and one of the ways we are trying to do that is trying to bring the students together. So when they're still learning, they can learn not just their own disciplines, but learn from other disciplines as well. And so that instead of like Mary and James and me trying to pick it up afterwards, they're getting some of it right from the beginning.
Well, I know that James has a picture of Kylemore on his website for his experience when he was out with us. And I just wonder, James, if you'd like to row in and when you gather at a place like Kylemore to do the research and to gather with your fellow colleagues, just to kind of give us some insights to working together as a team here on this call and with other people that Professor Kennedy has mentioned, and just sort of give us, from your mathematical perspective and the modeling that you do, how important it is to your work.
Yeah, it's critical. I mean, when I think of what I do with mathematical modeling of some physical process, I mean, ultimately it's just a model, and a model is really as good as what the inputs that you put into the model. So if you have, garbage input, you'll get kind of garbage output at the end of it. So in terms of, knowing a lot of the input, I certainly don't have the expertise for a lot of the, geological input that is really required to get a good output. Some of the stuff that I'll do might require, doing some parameter fitting, but then, I might say to get a good parameter fit, I would like this kind of data. And then it might be Andrew telling me, well, we can't really get you that kind of data. That can't be gotten. And then it's that kind of conversation of, how do you find something that works for both of you? What can be achieved by, what's the data that could be gotten, and how can that be put into a model in a good way? And then it's that kind of feedback loop as well that's vital. Yeah, very important.
A question that just came in through to me, and I this would be for all of you. I don't know who to direct this to directly, but it's with regards to technology, what sort of technology do you use, and is it expensive?
I'll start and say all levels from basically free, which is tape measures, to insanely expensive things like lidar and drones and many different levels. Mary?
Yeah, I would absolutely agree with that. The technology, there's been a huge leap forward in technological developments that the geological sciences have really benefited from, and that includes drone technology, the ability to build a topographic map down to the centimeter and the millimeter scale if you want, of one of these deposits. Some people might say, well, that's too much data, you don't need that much, and that's fine. But to get that kind of accuracy, it means that work is really speeded up now. You can do more of it, you can cover larger areas, and you can do it far more quickly. But in terms of, so that would be field equipment. We have these laser rangefinders that we can just, beam like a gun and shoot and find out what the distance is to cliff. We can use trigonometry to estimate the height of the cliff, all of that kind of stuff. But then we also have these very fascinating lab techniques, and this is more for geochemists like Melissa Burke, who's also one of our, no relation, but one of our teammates. And she's come up with some really intriguing ways of using kind of the geochemical signature that's left by critters or lichen or fungi on these rocks. And to use that in a lab, she now has developed this new technology that allows us to maybe date and find out the age of when that particular boulder was last exposed. And tomography is, where you can basically take an X-ray of rocks or trees or whatever it is and see what's inside. If you want to learn about, the source of where these boulders are coming from, if you took an X-ray of the surface, be able to see where the fractures are. So it's a surface in preparation for the next wave to come in and slam it and lift that boulder up. And so there's loads of technologies that we use and we plan to use in furthering this. And it's all for the good, I have to say, in terms of speeding up how we can get to the answer to our questions.
And I'll add that the UCD group with James and other people like Frederick Diaz is doing a lot of very high-level wave measurements in the west of Ireland. James, can you talk about that a little?
Yeah, certainly. Frederick Diaz's project is very much centered on wave measurements in and around specific locations on the west coast of Ireland, and that's from measuring the waves themselves, but also things like seismography and also weather measurements. So an actual weather station has been erected on the Aran Islands or near the Aran Islands. So there's lots of a wide range of very important parameters all being measured simultaneously in and around the same location.
And all of these are very useful for constraining the boulder transport problems.
Well, I will leave the last word to you, Professor Kennedy, or anyone who'd like to. Is there anything that we didn't get to that you'd like to mention for our call today?
I think we've covered a lot. I'll say two things. One is, if you get the chance to visit the west coast of Ireland, both the mainland, County Clare, and the Aran Islands, make sure you take the opportunity. It's a very interesting place, and you won't see any other place like it. And for you, Lisa, I'll say anyone who has a chance to visit Kylemore should also take the opportunity. And I have not been fed so well in a long time since I've been there.
Well, thank you. And all that's left for me is to thank you all, for the participants who zoomed into us, and for all the wonderful questions that our students and our participants gave to our panelists. Thank you for participating. A sincerest thanks to Professor Mary Burke and for Professor James Hetterich for being our guest panelists and for contributing to this Think Indie series. It's so important as being a part of Notre Dame International to show the work that our faculty is doing and our institutional partnerships that we have that are global. And so it's a great honor and privilege to have someone from Trinity and UCD. And I do remember Rona Cox actually saying to me that we need a weather station at Kylemore too. So that's on my to-do list, Professor Kennedy. But thank you, Mary, and thank you, James, for contributing to the series. It was highly enjoyable and much watched. So thank you again. And of course, to Professor Kennedy, you are always welcome to Kylemore and to be well fed and hopefully no wave sweeping over you. So thank you for your contribution, and a delight for Kylemore to highlight the work that you're doing, and truly the innovative work that you're doing, and how important it is, and how really uncharted territory we're in at the moment, and how important that your lab and the research that you're doing at Notre Dame and connecting with Trinity and UCD and our colleagues here, how important it is that we show such collaboration. So sincere thanks. So next week, we are traveling to our Mumbai Global Center, where we'll be seeing the impact of the rise of sea levels on populations in India. We have the videos up at the moment on the ThinkIndy platform, in which our professor from the School of Architecture, Professor Krupali Krush, will be interviewed by the director of the Global Center in Mumbai for next week's session. So please feel free to share this series with your friends and colleagues. We are accepting registrations throughout the entire program, and each meeting stands alone. So if there's an interest in another section, please, by all means, you're welcome. So signing off from Kylemore, we wish you a very happy Wednesday, and thanks again to all of you for joining.